Welcome to Vienna, welcome to ANTHOS 2024, organized by BNN, especially by my wonderful team. And I think we have a really bunchy start for this, so I will not further delay it. Enjoy the conference, and yeah, we will look forward to a very intensive 3 days.
I'm very happy to welcome you to the first full day of the ANTHOS conference. We are also streaming to online participants. Quick reminder to online people, it's a listen-only mode. So if you want to interact, your only chance is to write in the chat. Otherwise, we will focus more on the people that are here with us in Vienna, to also appreciate that you took the effort to travel and with us. We are very happy to welcome you, and I will start now with my introduction. Yes, so what is the overall topic of the conference, of this event? It's all about advanced nanomaterials and technologies, science, research and innovation for safety and sustainability. So this should already give you a hint what the topics will be in the next 2 days, and also the side events on the Thursday that we have prepared with the projects together. And for those who don't know me yet, my name is Susanne Resch. I work for BNN since quite some years now, and it's my pleasure to moderate the day for you. So to start, we said, let's give a quick intro to set the scene. So the topic is safe by design. What are the challenges and what are the potential solutions? Today is also the final event of 4 projects, the NMBP 15 project, Asina, Sabina, Sabidoma, and SbD for Nano. And they really focused the last 4 years on safe by design and how to address this topic in nanomaterials, nanotechnologies, nano-enabled products development. So something that is totally new for you, I'm sure you've never seen this ever. No. To start with, I just wanted to remind you how is risk defined. And it's risk equals hazard times exposure. I mean, this is nothing new. We do this in chemical risk assessment since years. This is still valid. And so you have to think about potential hazards, you have to assess potential exposure, and then you can see if there is really a risk or not. In Safe by Design, we try to do it proactively in a different approach. So Safe by Design is really to minimize hazard and exposure, to also maximize the safety, already in the design phase of either materials, processes, or products. So how can this be done, or what is the aim there? So it's really to increase knowledge about potential toxicity and also design out toxicological properties and modify materials if possible. So this would be more the hazard side. Or also to look at the processes, optimize them, avoid materials release during the use phases, change process parameters and settings. So to look it from the process angle. And this all of this while keeping the envisaged functionality. Then also, of course, it's always nice to keep any costs as low as possible so that it's also implementable in reality. And then it should be done as early as possible in the research, development, and innovation phase to prevent late development failures. Sounds pretty logic. I think if you see this in one slide, you say, okay, yes, I agree, of course. This is how we want to do it. But we can say the devil's in the detail. It's not that easy in reality. So you can look at this from the safe by material design perspective, or also from the safe by process design perspective, with the overall aim to have safe by design advanced nanomaterials. And again, as early as possible, considering the whole life cycle of the advanced nanomaterial, and also keeping the functionality and balancing the costs. So this is more or less in a nutshell what also the projects tried to address in the last 4 years of their runtime. Then if we are in the topic of nano, advanced materials, etc., we have some challenges that we need to also think of and address. I think it's also nothing new, just to remind everybody what are the challenges. Of course, it starts with characterization. You have to know what material exactly you're dealing with, what are the physical properties, shape, size, whatsoever. I mean, nano can be anything, so you have to be sure what really the material is. Then, of course, the toxicity assessment and the biological interaction might be different, and also the methods and tests that you have might need some adaptation so that they're suitable and that you get the right data. Then also the exposure assessment is somehow challenging because of these specific materials. Then the applicability of methods and measurement techniques, available standard test guidelines to get robust and reliable data, and also how to interpret them. Then also the access to existing data and knowledge. And as I said before, levels in the detail. Usually each case is slightly different. So this topic of nanosafety, of course, is not new. I picked some highlights. So this is not holistic. I just picked some highlights from the history. So already in 2005, the nanosafety term was coined. And in 2010, the EU nanosafety cluster was established. Quite some time ago, if we see these numbers now. Then in 2013, it was the NanoRec project that also really worked hard on this safe by design concept for nano. And then we had follow-up projects, NanoRec 2 and ProSafe, that they tried to really test the application of this safe by design concept with industry. Then in 2017, the Malta initiative was established. That is also an important OECD link to modify and adapt the OECD test guidelines for nano. And then in 2019, the NMBP 15 call topic was launched. And what were the topics from this call topic? So the title was Safe by Design from Science to Regulation, Metrics and Sectors. And the aim was to develop new safe by design methods that enable reduction of hazard and exposure without affecting the material performance and guide development of safer products at different stages. Then also to apply control measures and mitigation strategies for nano-specific scenarios in different industrial sectors and develop computational approaches to model them. And last but not least, also to implement safe by design approaches and tools at an early stage of nanomaterial development process. And then we had 4 lucky projects that got the win in this call. You see here really only in a nutshell, it was the ASINA project coordinated by Ana Costa from CNR, then Sabina coordinated by Soko Vázquez Campos from LITAD, Sabidoma coordinated by Andrew Nelson from University of Leeds, and SbD for Nano with the coordinator Carlos Fito from ITENE. Outside of the room, we have also project corners that all these 4 projects have materials that they want to show, videos, flyers. So please also use the breaks to engage there at the project corners and see what the projects were doing in the last years. Today, we try to really show you highlights and outcomes and results from these 4 projects. But of course, I mean, you see here the number of partners and the budget behind. There were many, many activities that the project did, and today we cannot give you the full picture, but we tried to focus on the key results. And if you want to learn more, please also talk with the colleagues at the project corners outside. So then the project started, and slightly before also the European Green Deal was published. Then 2020, you see the start of these 4 projects. Shortly after the European Chemical Strategy for Sustainability was released, and also a new generation of projects, NMBP 16, started. Then it was also in 2022 that the Commission published a recommendation on SSbD. So you see already a second S, the Safe and Sustainable-by-Design concept. And then we also had new initiatives and activities from PARC and IRIS, as many others, but I picked them because they will also play a role tomorrow. So tomorrow we hand over to the new initiatives that tackle these topics. So we will have the NMBP 16 project and PARC and IRIS. And 2024, finally, here we are at ANTHOS. So we have 2 full days, today and tomorrow, packed with many presentations from experts from the different projects. We start soon. I will not talk too much anymore. We start soon with the first session, Safe by Material Design. Then we have a coffee break. Then we have Safe by Process Design, followed by 2 short sessions about sustainability aspects, including functionality and costs and legal aspects of Safe by Design. Then we go in the lunch break. And then we have also a long session about Safe by Design tools and technologies for nanomaterials. This is really one key session because it will show you the tools that were developed in the projects. Then we have another coffee break, and then we have time for 1 hour case study presentation. So all projects had industrial case studies. So I think it's also nice to see how industry perceived the whole process and what they learned and what they could achieve. And then we have a nice roundtable discussion, closed then by a networking dinner. So I hope you also all use the chance to discuss and chat with colleagues, network, maybe find new ideas for new projects, etc. Tomorrow we have another full day that, I will not go into detail because it's not relevant now. And with this, I think I can close my introduction and start the very first content-related session, Safe by Material Design. We have 4 speakers in this session. And the first one is Ana Canalica from LITED, the Technological Center LITED in Spain. And she will talk about hazard assessment strategy towards safer development of nano-enabled products in SbD Safe by Design guidance platform. So I think with this, I can already hand over to Anna. That's a very good question. We are streaming and recording, and if the presenters agree, we will also make the presentation slides available afterwards. So our plan is to, also on the website, there is a full book of abstracts. I don't know if you had already a chance to have a look at it. It includes CVs of all speakers, short abstracts about the sessions, and our idea would be to link the slides directly to the talk then in the book of abstracts. Of course, if presenters agree. We don't publish anything that we're not allowed to.
Okay, everything's ready. Good morning, everyone. First of all, as I'm the first one talking about SbD project today, I want to do a brief introduction to the project for those of you which are not that familiar with the project. So the SbD guidance platform is an overarching, integrative, and interactive web-based guidance service that aims to support industry in the design of safer nanoforms, safer nano-enabled products, and safer nanoprocesses over the whole life cycle. And it is tailored to different industrial sectors, paints, and 3D printing. The platform is built upon the existing tool, Guide Nano tool, and it has different modules of assessment. It has exposure model, hazard, sustainability and cost, and product performance. All of that to identify and implement Safe by Design interventions towards safer products and safer processes. Also, the platform streamlines different existing resources such as databases, templates, fate models, risk assessment tools, and hazard strategies to guide the industry on how to use them for SSbD purposes. So a critical part of this platform is the human hazard assessment. It's comprised of 2 different phases of increasing complexity. We have a first screening phase in which we gather information on the CLP classification of the nanoform and the physicochemical properties, and also the expected exposure routes. And then in a more detailed second phase of assessment, we will retrieve additional hazard data from already existing data in databases, or generate our own new data following some strategies that I will present you. Then based on that, the platform analyzes the situation and raises different flags depending on the different levels of hazard concern. So we will get green flags for low concern situations where no SbD intervention needs to be implemented. We will have red flags for high concern situations, and then we will suggest SbD interventions. And we'll have also yellow flags when there's moderate concern or not enough data. In this case, the user is asked to look further into potential exposure and release. So the main aim of the strategy is to identify potential hazards at an early stage of product development, preventing in this way the user from large investments in money and time, and to guide the industry towards safer by design interventions in a pre-market and pre-regulatory situation. Regarding the screening phase, in here we want to ask the question, are there any known expected hazard concerns which already hint on a required SSbD intervention? This phase is built on as an early warning system. It requires minimal information from the user, and the aim is to filter out nanoforms of high concern and identify data gaps. If you get a green flag in here, the user can exit the platform. Otherwise, if you get red, yellow flag, you can go to a more detailed assessment. Regarding the information we require in this phase for hazard, it's related to the physicochemical properties of the nanoform. And this is the list of inputs required. It's about composition, EC or CAS numbers, crystallinity, morphology, size distribution, surface area. And then the platform can raise already some obvious hazard warnings, such as presence of rigid fibers with a high aspect ratio or use of crystalline silica nanoforms, for example, and also hazard warnings based on the CLP classification to detect substance of very high concern or high concern. The platform has an internal database built in with public information from ECHA and other websites. This information can be automatically retrieved only using the CAS number. And this is nanoform-specific information, and also then the assessment is performed accordingly with the JRC SSbD framework. In the second detailed hazard assessment, this included tailored hazard strategies for inhalation, dermal, and oral exposure. It also includes guidance on how to retrieve data from different databases and also on how to generate data following batteries of different toxicity tests. And also during the project, we optimized several assay protocols for higher efficiency and applicability to nanoforms and nano-enabled products along the life cycle. To do so, we first identified existing resources, databases, tools, testing methods suitable for the prediction of these key hazard endpoints. These strategies are built further upon the IATAs developed in the Gracious project. Also, the toxicity endpoints were selected to cover as many known nanomaterial-specific adverse outcomes, mode of actions known. And the toxicity tests selected were based on their simplicity, the affordability, and the existence of standardized approved protocols, and also on their robustness and predictivity. And finally, also meaningful thresholds of concern levels were set up for each toxicity endpoint, and those are based on previous work that was done during the NanoReg2, ECHA, NanoApp, and DF4 nanogrouping projects, and we further developed those thresholds using several different benchmark materials. The main challenges we encountered when building these strategies were first understanding the relationship between the physicochemical properties and the toxicity. And this is very important for us to be able to really link hazard information to a tailored SBD intervention. Also understanding how these properties can change the properties of the nano-enabled product during the life cycle and how this will affect the toxicity. Then how to combine the hazard information and weigh the different toxicity endpoints to deliver a final hazard outcome, and how to handle conflicting results in the testing strategies. Then on another hand, in a more technical way, when running our hazard strategies, we also encounter some other challenges. Therefore, we ask the user before starting to gather information on the mode of action of the nanoform they want to assess, then also to choose an appropriate benchmark material that will be included in all the testing. This benchmark material ideally should have the same core chemistry, same expected mode of action, and known in vivo response. Then also the user needs to decide if it's interested in testing the nanoform or the nano-enabled product, and if testing the nano-enabled product, consider which life cycle stage is interested in studying. Then also basic physicochemical characterization should be performed on the material to determine the stability and dispersion, the position factor, and overall the suitability of the material for testing. And this will then influence also the selection of relevant cell lines for the exposed organs, and also the selection of an appropriate exposure method, for example, in submerged cultures versus air-liquid interface cultures. This is how the build strategies look like. Here we have the strategy we built for inhalation hazard, and here the strategy for thermal hazard. In the case of inhalation, we gather information on the dissolution rate on simulated lung fluids, cytotoxicity, genotoxicity, ROS generation potential, and inflammatory potential. And then for the thermal hazard strategy, we add some extra endpoints based on skin irritation, corrosion, and absorption and barrier integrity. Then for each one of those nodes, we apply thresholds to classify the levels of concern of the nanoform depending on the results we obtain. So to link these hazard warnings, we will get to specific tailored SbD interventions for minimizing this hazard. We first perform a data gathering on the different SbD strategies that have been successfully applied in the past. This is a summary of the different most common interventions that were applied that we classified in 3 different groups: modification of physical-chemical properties, resizing, and modification of surface properties. And then to correlate this hazard to a safe-by-design intervention, we first need to identify or hypothesize the mechanism of action induced by this nanoform, associate this mechanism to the toxicological endpoints we are assessing, then determine the physical-chemical drivers of the hazard, and finally define the location of these hazard driver properties in the nanoform, if they are in the surface or in the core of the nanoform. This table collects some of examples for different toxicological endpoints. We describe different mechanisms of hazard mode of actions and relate them to the surface or the core of the nanoform. We also describe which are the most likely physical chemical drivers for that and suggest some SbD interventions. Then what is good of these strategies is that you can use the same toxicological endpoints to test again the SbD implementation and see the effectiveness. So to demonstrate our strategy, I will present one of the case studies in the project. This one is based on the use of colloidal silica for outdoor paints. First, we will see an overview of the life cycle, starting with the design and the development of the nano additives. In this example, our original nanoform, it's going to be colloidal amorphous silica nanoparticles. And the SbD intervention suggested could be silane modified silica. For the sake of the example, I'll simplify and use only one modification, but in the case study, we have different silicas with different percentage of silane. These nano additives are added to increase the stability and for longer storage of the paints, and also to add anti-fouling and anti-soiling properties. Regarding the manufacturing, we define our nano-enabled product as a paint formulation functionalized with colloidal silica, and we analyze different occupational scenarios such as weighting, mixing. For the service life, we consider professional consumer scenarios like the spraying of the paint onto planks, for example, and other release scenarios once the paint is applied, like watering, wiping, sanding. And for the end of life, we consider mechanical disposal of the paints and leaching scenarios. So in this way, we can see that the most likely exposure is going to be by inhalation or thermal contact. So what questions we want to answer with the Sabina platform? The first question would be, are there any known hazard concerns with my current nanoform, the silica standard, simple colloidal silica? And the second question would be, how well does my SbD implementation perform in terms of hazard compared to the original nanoform? And for the example, I'm going to focus on the inhalation hazard strategy. The first node in our strategy was a dissolution in simulated biological fluids. In this case, we used dissolution in a cellular system with lung cleaning fluid and phagolysosomal fluid to gather a mechanistic insight on the toxicity coming from ions or coming from particles. This is based on gracious work. And what we have is that for both of the silica forms, The outcome is that they are gradually dissolving, and then you have to consider both ionic and particle toxicity. This data is retrieved from eNanoMapper. In the second node, we assess cytotoxicity. In this case, we tested in vitro different exposure methods, submerged versus air-liquid interface. In this case, for example, we decided air-liquid interface was more convenient because of the different deposition factors of the two silica, the standard silica deposits and the other one not. And we use different cell lines and different cytotoxicity assays, LDH, WSC1. This is just some of the results we got. And the outcomes in this case is that the silica standard classifies as high cytotoxic potential regarding the IC50 value and the dose response. And the silica selene classifies as low cytotoxic potential. Next node is genotoxicity. In this case, we combine the outcomes of two different readouts, the micronucleus assay following the test guideline and the 53BP1 assay. And in this way, we find that the silica standard classifies as moderate genotoxic potential in vitro. And for the silica selene, we also get the same outcome. For raw generation potential, we combine also two different kind of tests, and a cellular test, such as the FRAS assay, for example, and another cellular assay, the CFH or protein carbonylation, for example. And then the outcomes we obtained was that silica standard showed a high ROS potential in the DCFH assay, and silica selene showed low ROS potential. For the inflammatory potential, again, we tested different cell lines, different exposure methods, and we measured the expression of different pro-inflammatory cytokines by ELISA or qPCR. And this is some of the data we gather. So for the standard silica, we find high expression of IL-8 by ELISA and also qPCR. So it classifies a high inflammatory potential. And in the case of silica selene, we don't have sufficient data because we couldn't test in the same kind of assays, so you cannot really compare. So we just leave the insufficient data here. And this is how the final hazard outcome looks like, combining all the different endpoints with the different flags raised for each one of them and the final hazard outcome. So the conclusions is the silica standard show high potential for cytotoxicity, ROS generation, and inflammation, and moderate genotoxic potential. Then the SbD alternative, the silica selene, succeed at reducing cytotoxic and ROS generation potential and fail at reducing the genotoxic potential. So overall, we can say that the toxicity endpoints assessed show improvement in the final hazard score. Then the user should, with this information, with the results coming from the exposure, functionality, sustainability, and cost modes, and decide if it's worth the SbD intervention. Also, to validate the predicted capacity of our strategy, we compare these results with in vivo results previously generated in ratios for in vivo studies for chronic pulmonary inflammation. And what we can see corroborates our findings. The silica standard here, it's more potent in inflammatory pulmonary than the silica selene. And finally, just some take-home messages that I want to deliver. First, that the developed human hazard assessment strategy provides the industry with useful guidelines and tools on data gathering with a set of easy-to-use, robust, and cost-effective testing approaches for the prediction of potential nanoform hazards. Then the low-tire in vitro assays targeting toxicity endpoints that combine common key events relevant to different multiple adverse outcomes are useful for capturing the potential of the nanoform hazards and can be used at early stages of product development to prevent the user for large investments. Then also important that the hazard strategy aims to be used only for SSbD purposes, and it does not replace in any case the regulatory requirements for testing before commercialization. And finally, that this early warning system can support the implementation of safe design on nanoforms and nano-enabled products, and it's compatible with early stages of product development and along the whole life cycle of the material. And that's it. Thank you for listening, and I'm happy to take any questions, comments you may have.
Thank you very much, Anna, for this nice presentation. We have time for 1 or 2 questions. Martin, I saw you first.
Thanks for the presentation. I saw the SSbD scores. Can you maybe quickly show how you scaled the scores? They looked good, but how did you scale it?
Yeah, it's still controversial. We had long discussions about it and still defining the last bits of it for our deliverable. But the main idea could be that we add some sort of a extra +1 point for improvement from red flag to a yellow flag, for example, 2 points from the red flag to the green flag, and we sum up all the different points. We can also combine, for example, dissolution information with rust production and inflammation potential, for example, and all of that combination will give an extra point. So this could be the way of combining it.
Great, thank you. There is another question. Maybe Wendell first, and then Andrew, and then the next speaker.
Wendell Wollin from BASF. This looks very logical and nice. I was just wondering about the resources needed to perform what you just presented, because you say it's for early stage development. So can you estimate the person months or person hours that went into establishing the data that you presented?
Well, that was quite a bit. Now it's optimized, so it should be less for the user. But yeah, it's still quite an investment on in vitro testing. Still, obviously, much less than what you can invert on higher testing. But yeah, it's a collection on many different endpoints. But I think it's necessary to really capture different mechanisms. The strategies are also hierarchical, and the user can stop at any point of it, so it can gather information only from cytotoxicity and genotoxicity, for example, and it may have enough with that, so it doesn't need to continue the full strategy till the end.
Great, thank you. Andrew?
Nelson Leeds. I have to say that's an extremely interesting talk. Thank you very much. A double question. First of all, what's the particle size of the colloidal silica? And secondly, how do you salinize it? Extremely interesting. Thank you.
Oh, those questions probably can be better answered for my colleagues giving talks after me, because I'm more a specialist on the toxicological side of it. The size of the colloidal silica, sorry to point you. Around 11 I don't know, meters.
With this, we can move on with the next speaker. It's Rosella Bengali from the University of Milano Bicocca in Italy. And she will talk about an integrated new approach methodology for risk assessment of SSbD nanomaterials.
So good morning, everybody. Thank you for this opportunity. Okay. So today I'm going to show you this NAM framework for the risk assessment of safe and sustainable by design materials this framework was developed in the ASINA project. So we all know that one of the aim of the SSbD framework, the main aim is to minimize or eliminate as much as possible the impact of human health and the climate on the environment along all the chemicals and materials entire life cycles. Of course, that poses several challenges, because when we have to test the hazards along the different stages of the life cycles, there are different methods. We can't apply the same methods for the synthesis phases for the manufacturing or for the use phase of the products. And we know that for testing and demonstrating this SSbD framework, the data should be generating using as much as possible NAMs, so new approach methodologies that should be also included in the case studies. So we have a different, you well know better than me that there are many key points. So we have case studies, we have SSbD, and we have also NAMs that should be included in this framework. So the state of the art is well known about the limitation of the hazard assessment of nanomaterials. So for chemicals and for nanomaterials are often used animals with a realistic doses and method of administration that are not corresponding to the reality, then we use a lot of simple in vitro monoculture model in submerged conditions that are very helpful for getting information on the mechanistic of the nanomaterials of the chemicals, but are scarcely representative of the in vivo situation. Also, the doses uses are high, up to 10 micrograms centimeter square, or also the metrics are not so realistic and relevant for the exposure scenarios. And there is also difficulties to in investigating the real exposure scenario. For example, when we have to investigate the hazard during the production of a nano-enabled product. So there is a need to shift towards a new risk assessment methodology for nanomaterials, and the new approach methodologies are able to provide this information without using animals. So we have different reasons to use these names that are ethical, scientific, and practical reasons. And these new approach methodologies are strategies based on in vitro, in silico, or in chemical methods that can provide information on the hazard and risk assessments of the chemical. And here we have some examples. So in vitro culture, but also advanced in vitro models, the use of high throughput methodologies of several biochemical or also imaging methods, the use of IOPs in assessing the hazard of nanomaterials and in silico modeling. So here we have a case study specific for the ASINA project that aims to the hazard assessment of silver-based design alternatives through the SbD approach, considering the inhalation as a primary route of exposure, and we use a NAM. So the case study is specific to the spray coating of textile with silver nanoparticles. Here we have different alternatives, design alternatives of silver nanoparticles. So we have silver naked, so without any coatings, and silver nanoparticles that are coated with the hydroxyethyl cellulose and with curcumine to increase their functionality, so to increase their antibacterial potential, but also to increase their stability, because we have to remember that all these nanoparticles has to be functional, so they should be incorporated in the process, so they should have specific characteristic. All these nanomaterials were characterized for the size and the surface charge, and then the in vitro hazard assessment was performed through monoculture of in vitro lung cells. So in order to investigate the silver nanoparticles toxicological outcomes following an IOP testing strategy, and then the co-culture model of the alveolar space was exposed at the liquid interface at different realistic environmental doses. So first of all, the biological evaluation was performed on an adverse outcome pathways strategies. So we have characterized the nanomaterials. As you can see, they have different properties with the silver naked nanoparticles with high dynamic hydrodynamic, and with the silver curcumine with the lower diameter, around 100 nanometers. And then they have different surface charge with the silver HEC being the positive nanoparticle and the silver curcumine being a -1. Then we tested this nanoparticle using a simple monoculture model over 5-4 night. We use the concentration, different concentration in order to have a responses curves. And we have investigated different toxicity endpoints, which are observability, inflammation, oxidative stress, and DNA damage, that are all included in a adverse outcome pathways that has as final AO the lung dysfunction. So what we have seen is the interaction of the cell with the nanoparticles, and also to have also a scoring of toxicity of these nanomaterials. So as you can see, when we have higher low interaction of the nanomaterials with the cells, we don't have the production of rust, the inflammation, and then all the other key events of the pathways. So the scoring is low, it's 1. Then we have that when we have a high and significant interaction with between the cell and nanoparticles, we have an increase of inflammation, also a high oxidative stress and DNA damage, so a higher score of toxicity. So this is the toxicity of the nanomaterials at their synthesis phase. When we move towards a production phase, we were able also to provide evidence that through this nano approach, there is a lack of hazard of these new nanomaterials. And why? Because we have started to collect and to measure at a specific production site. So during the spray coating of the material, the particle number concentration of the material that are at the occupational sites, so that are relevant, they are realistic of the exposure of the workers. Then these measurements were used for calculate the alveolar retained dose through a computational model, that is the MPPD model, in order to have the realistic exposure doses that were then used with an advanced in vitro model that is based on co-culture of A549 tests and macrophages. So we can also see that, of course, we started from micrograms ml around 1, our maximus was 100. Here we have that the concentration are really, really low, that the highest concentration that we reach is around 200 nanograms per centimeter square. That is corresponding to the a chronic exposure up to 1 year of exposure of the worker. So this approach also allowed to have not only acute responses, but also the chronic responses. That is another main challenges when we have to deal with the exposure to nanomaterial. So this framework, it's about the safety evaluation based on the relevant realistic exposure doses, scenarios, and toxicological endpoints. So this is the model that we have used, so the co-culture model that was exposed with the vitrocell cloud alpha, so the nanoparticles were nebulized at the different realistic doses, and then cytotoxicity with LDH and inflammatory mediators were analyzed, and we didn't observe any decrease of variability of any inflammatory response of the co-culture after the exposure to occupational doses corresponding to 1, 6, and 12 months of exposure. So this was specifically related to the HASINA project, but as you can imagine, this approach could be also transferred to other and apply for other cases, such as for the production of polyurethane foams. So here we have the production of the polyurethane foams and the different instruments used for the measurement of the nanoparticle release during the production process at near field, but also at far field, so in different spaces of the occupational space. Then the data are used for the lung deposition modeling, and then in vitro exposure ideally could be also improved using not only the nebulizer system with the vitrocell, but also using a direct exposure with the Caltex RFS module exposure that allows to have a direct exposure even when the production is ongoing. So it's possible to directly measure at the same time in the release and the exposure in vitro. So of course, this framework has a different target users. So not only the scientific community, but is also interesting, in our opinion, for regulators, policymakers, for the occupational safety managers, but also for the designers, because we can support them in order to help them in the safety of their materials, but also of their process. And this framework contributes in limiting occupational exposure. It's more predictive for the hazard assessment and realistic, and it has no ethical implication. So some take-home messages: the SSbD approach through the use of the the new approach methodologies provides realistic and reliable data on the hazard of the new chemicals, but inclusive also nanomaterials, and should be also included in the human regulatory toxicology. So thanks to this framework, we are able to say that silver nanoparticle induces responses that varies depending on the different nanoforms and models, but this is good because at this phase, the designer could also change the synthesis in order to have safer alternatives. We have provided information about the safety, so there is a lack of hazard and exposure risk for realistic doses. And then this framework is transferable, but it needs to be validated through other case cases, of course. And the future perspective is to explore more in detail other toxicity endpoints typically associated with the nanoparticles through also the integration of the omic approaches. And I want to thank the ASINA consortium that allows us to develop this framework, and also to the next project that will allow us to validate it, to see if it works. And also to my team in Università Milano Bicocca, the Polaris team, that of course helped me a lot with this work. And all of you for your kind attention, and I'm ready for the question. Thank you.
Thank you very much, Rosella, for this interesting presentation. We have time for questions. Yes, first question there.
Stefano, University of Ferrara. It seems to me maybe I lost that your model, which is a nice model, didn't take in account the time of flight of the particle within the respiratory system. We have investigated using, in collaboration with the University in Australia, the time of flight, because it's very important to know how long it goes. And so we use a kind of model of the respiratory system. Mm-hmm. So it's like the respiratory system. And so I'm just wondering if you may agree that this could be a further approach in your...
Yeah, I think that for the nebulizing process, we miss some information. And with the Caltex RFS, we are able maybe in the future also to consider this delay and this more similar, more realistic to the in vivo scenario, how the particle deposits in the lung. Because with the nebulizing, there is only gravitational settings, and this is, of course, a problem.
Correct.
And the challenge is to use in the future also diffusion and all the other processes that are involved in the deposition of nanoparticles. Thank you. Of course. Thank you.
Thank you. Another question?
I'm Roland Grafström, Karolinska. So I'm a happy co-author of the Schmeischer paper that you showed. And so then one question, of course, will be applicability domain. You know, you have one, and I think you mentioned in sort of your last sentence to show the validation. So that's one question, but a more specific question then would be, you had also an AOP directed approach with your in vitro methods, but did you also consider to take it further, looking into the AOP wiki and, you know, substantiating it into specific AOPs?
Yes. Yes, thank you for the question. So I think that we have to take in mind the tier approach also for advanced in vitro method, and to go further. So not only on the lung dysfunction, what I think it's important for the AOPs, but this is my opinion, is that if we put them together, there is a network of them. So there is a network of key events that are specific for different AOPs, but that are really relevant. So I'm also happy to see that when Anna before me showed genotoxicity, inflammation, cytotoxicity, and ROS. So I think that we should, with the omic approach, also investigate more in depth at higher tier level. So with the more complex in vitro method. So here we have only two kinds of culture, but of course we can implement other macrophages, monocytes, other endothelial cells in order to have a better comprehension of what happens at the alveolar space when dealing with nanomaterials.
Great, thank you. I'm also reading now one online question. It's could you compare the cost of using NAMs comparing with complete lab analysis?
I have
a challenging question.
Yeah, no, I have to say that there is a huge challenge if we consider the process and that we have to deal with the material, with the instruments that are really expensive, but also we have to transport them. So there is a trained person to do all the analysis. So I think it's not comparable. So by now it's not so comparable.
Okay.
Yeah.
Great. Thank you very much, Rosella, once again. And our next speaker is Maria Duszinska from NILU, Norwegian Institute for Air Research in Norway.
Climate and environmental research. We changed the name.
Ah, you changed. When?
That was
My research.
recent.
Okay, it seems that my research was not
Can
correct.
you hear me? Yeah.
Yes, and she will talk about the SbDoma SOPs and tools for risk assessment. Maria, it's a pleasure to have you.
Thank you very much. Good morning, everybody. I am very happy to present some of the achievement and work of SbDoma, but also reflect some results from collaborative project RISGON. And in my talk, I will mostly focus on regulatory relevant challenges with risk assessment of nanomaterials, such as dispersion or interaction of nanomaterials with biological system, and also will highlight some problems regulators have with reliability and relevance of studies, so with the data reporting and quality of data reporting. And finally, I will focus on SbDoma approach to safe by design to implement risk assessment early in the development of products. So you saw this background of from Suzanne. She set the scene about what risk assessment is, and the risk assessment for chemicals also applies for nanomaterials, because nanomaterials are specific groups of chemicals. So it has these four main pillar: hazard identification, characterization, and dose response, and exposure assessment and risk characterization. Of course, it's always important to balance between risk and benefit. And this is a risk management tool. But as we all know, there are many challenges with nanomaterials risk assessment, and one of them comes that we don't have still unified definition what nanomaterials are, and also we have several generations of nanomaterials and advanced materials, so it becomes a bit complicated. So also you already saw the history about how actually not only research but legislation developed during these years, and there were several important documents issued and several legislation. I would not go through all of them. For example, there was a first definition in 2009 for cosmetic regulations. There were several guidance documents developed. Important is ECHA in 2017, a registration dossier, and also labeling, two guidelines, guidance document from EFSA and SECS, the Consumer Safety Committee, which implemented lots of scientific knowledge. But as you could see, the risk assessment of nanomaterials is sector specific. So there is not unified legislation for risk assessment of nanomaterials. So how it was with research, also Susan already showed some of the history of nanosafety cluster development, but also with which started actually with Framework Program 7. And also before in Framework Program 6, there was one or two projects which were focusing on nanosafety. And in this first period of research in Europe on nanosafety, FP7 projects focus on mechanistic way to understand behavior of nanomaterials with biological systems. And there were lots of standard operating procedures and protocols developed. And also first challenges, immediately with starting the research, there were these challenges already identified. And later on in FP7, there was idea of safe by design developed, and as a representative, it's a NanoRec project. And then later in Horizon 2020, safe by design was fully addressed in many projects. And here we are with NMBP 15 projects and then also NMBP 16 projects. Now we already started Horizon Europe, and the topic and focus on Horizon Europe continue with safe and sustainable by design, but not for specifically nanomaterials, but in broader perspective for advanced materials and chemicals generally. And the reason for it is that also in a regulatory area, regulatory landscape changed. And you could see in the last 5 years already European Commission adopted many important documents, such as European Green Deal in 2019, then Chemical Strategy for Sustainability 2020, Zero Pollution Action Plan 2029, and then also important documents on JRC on safe and sustainable by design, and framework for European framework for safe and sustainable by design. And now recently one substance and one assessment, which really also from the regulatory landscape, there is a huge effort for harmonization and unification of legislation. So as I said, I will only address several challenges which regulators are faced with, and as I said, there is still a lack of unified definition of nanomaterials. There is no global regulation, but sector-specific. The challenge starts with characterization of nanomaterials and unique features of nanomaterials which change their properties depending on the environment they are present, forming, for example, protein corona, or they attract, because they are very reactive, they attract other molecules. So it's very difficult to handle and to have a standard conditions for hazard assessment. And of course, appropriateness of test methods and huge effort which actually started during all FP7 Horizon 2020 and now also in Horizon Europe for standardization and validation. Only I mentioned Nano Harmony, Malta Initiative, NanoMed, and also, for example, RISGON, which try to accelerate and speed up with OECD test guideline development. So and there are some documents issued, for example, this document from European Commission for risk assessment of manufactured nanomaterials. So there is from both sides, also from scientists, but also from regulators and European Commission the initiative to really implement the scientific knowledge and to unify and harmonize legislation. I will mention this on the background of our old results, which were actually 15 years ago in the nanotest obtained and published already on the background of this, where we actually use two different dispersion protocols, the monodispersed or dispersed to achieve stable dispersion, and also without serum with agglomeration, so more natural type of exposure. And we find out that actually the outcome of genotoxicity is different. This is with COMET assay results. And that also highlights the problem. For example, in titanium dioxide, recently EFSA evaluated it as a not safe, and Health Canada, Australia, New Zealand opposite evaluated it as a safe, and on the base of same open literature and same studies. A reason is that in Europe we prefer more more dispersed and stable dispersion to look at nanospecific effect, and in the Health Canada, USA, and Australia, more natural. And as I highlighted here, perhaps the best way is to combine these two approaches to conclude in the same way results. And another problem, which was also highlighted early in FP7 projects and with researchers almost 10-15 years ago, is the possible interference of nanomaterials with some tests, especially fluorescence and colorimetric assays, and it is based on the fact that nanomaterials can interfere with readouts system. And as you could see, there were many publications on this topic in around 2010-15. And the finding that even without cells, there is a so-called positive effect. So to avoid the false positive results, it is really important to include so-called interference controls. And recently, within RISC-ON project, we actually review literature. Sorry, and not only to summarize which assays can be problematic, but also we propose decision-free for checking and mitigation of the action to guide the users how to check the interference and what to do if interference is found. So either to do methodological changes or finally change the assay. And this is this decision tree is cloud platform, which is actually the same as the shared, not only RISC-ON, but also SbD. And the paper is now actually in press in Nano today. So another important issue is how to report the data. Risk assessors, because there is not enough test guideline for specific for nanomaterials, even there is a huge effort and speeding up with this implementing and adopting on modifying existing test guidelines, but also developing new. There is still not unified and harmonized way how to report the data. And then, of course, risk assessors look at the open literature, and sometimes even very good studies are considered as with low relevance or not reliable, on with limited reliability, because researchers do not report minimal essential information. And this we actually addressed, and I just highlighted here several efforts and several templates which were already which are in place, such as OECD harmonized template, but this is supporting Euclid 6 for chemicals. This is not specific for nanomaterials. Then later on, ECHA, Nano, and different versions were used and developed, and also used in, for example, NanoRec. And also there was another effort from Institute of Occupational Medicine, ION from Edinburgh, where they developed a really very good user-friendly template, and that was used with many FP7 projects such as Nanotest, Marina, and others. But from the knowledge from all these templates, we developed the IDEA partner developed the template wizard framework where harmonized templates are available, and these are designed co-created together with researchers. So it's very good user-friendly template and provides streamlined process to develop metadata data and harmonized data capture templates. So it can be widely used and also reused in different area, not only in nanosafety, but also for advanced materials and also for chemicals generally. And these templates are citable, so they have license. They are available either in Template Wizard or in Zenodo, so they can be used, and researcher can co-create their own templates. But these templates are really the harmonized, so there is an identifier for nanomaterials and materials, spreadsheets with all information. This is how data entry templates are converted into this data model. It is the machine learning a tool, and it allows to better evaluation and comparison of data. This is as an example how it is designed. So all crucial information should be included, and also helps to researcher to design their study properly, and also not to remember to include important things such as controls or specific media or cells and sources. So finally, it can and also it includes raw data and automatically calculates the results. So it minimizes this mistake. These harmonized templates are fair themselves. And already already there are 74 templates available for physical chemical characterization, human hazard, ecotoxicology, and this is the way how you can actually co-create a new template or reuse existing template. And recently we got actually accepted paper in Nature Protocols, and the first and last authors of these papers are from SbD project. So finally, I would like to mention how the SbD approach to safe by design and implementation risk assessment into early development. As we know, TRL or technical readiness level was developed already in 70s last year, and used first in NASA, in space, and also in defense products. And in 2013, it was the ISO published with 9 TRL steps, and in Horizon 2020, this approach TRL was implemented into Horizon 2020 after the recommendation from high-level group. And SbD approach is that this safe by design should be implemented in parallel with TRL development. So we have 3 groups of TRL, basically initial development, proof of concept from 4 to 6, and from 7 to 9 demonstration. And in each of these level of development, there is a set of guidance documents. First, the characterization of possible hazard and identification, and if possible, exchange or use alternative material for development of product. Then in the second group, the proper hazard characterization and quantification of the hazard. And in the third group, in demonstration, also focus should be on setting limits, and also precautionary principle for handling materials, as well as to develop set of SOPs for proper waste and in the life and risk in the whole life cycle. So this was also implemented as a guide in the SbD Cloud platform, and I hope it's available for users already now. So as a conclusion, I would like to highlight again that really it is important to implement new knowledge into regulation, and science is always ahead of regulation, because legislation is not that flexible. Also now from the European Commission, it is a need for harmonized legislations, one substance, one assessment approach. Fair data and proper data, harmonized data reporting. It's really important, and it's also good for researchers and important for regulators to have access to good data and properly reported data. And of course, there is a need to speed up still this validation of new advanced model and also standardization and development of new test guidelines. But implementation of safe by design approach into regulation, it's really challenging because risk assessment is pre-market. So it's important, or it's obligatory for developers to do risk assessment for product which should be marketed. So implement it with early development, it's a challenge, but still it can speed up also market process. Last but not least, within nanosafety cluster, there were huge amount of data and new knowledge generated, and this shouldn't be lost, but should be applied for the advanced materials and chemicals generally. And last but not least, I would like to acknowledge to my coordinator and coordination team from University of Leeds, Andrew Nelson, IDEA colleagues who developed or helped us to co-create these templates, Nova Mechanics for cloud platform, and I only included task leaders from our work package 6, Ignacy and Anthony, and of course, but the work is from all SbD consortium. Last but not least, to risk gone consortium, especially Ivana and Isolde, who helped with this data template and also this interference paper, and to my colleagues from Health Effects Laboratory at NILU. Thank you very much.
Thank you very much, Maria, for this presentation. We have time for one quick question.
Thanks. Fantastic overview. So you mentioned machine learning, and would you take? It might be not a short question, but a long answer. But how do you see on AI and machine learning then in taking on this challenge with all the data?
Yeah, I think it's really now the time to use artificial intelligence and to use the tools we have, because it will, every researcher can based on the test or method or study, co-create together with technical expert own template, but it will be harmonized and connected, so you can really extract information. For example, when you test one nanomaterials, you have all identifier, class numbers and everything, and all characterization, and you can also look at which test and what was done. So it's really dramatically increased meta-analysis, and also if because I try to focus from the regulatory perspective on this, that would also help regulators to do better risk assessment.
Great. Thank you very much, Maria. Further questions in the coffee break then. Thank you.
So why surface chemistry? Because the concept is safe by design, but can we really design it? I mean, that's the issue here, because we are dealing with a material which is the group of materials which is not really designable by nature, because you will see not working. Okay, that's fine. So because when I like to share with you this slide, then see, you tell me, is it too fast? Okay, yeah. So you tell me if this is, what you see here, is it really a designable material to you? When you start synthesizing these materials, I mean, you end up with something. Of course, they show unique properties, but really, because, safe by design, it starts from the R&D stage. So you need to think, of course, as a chemist, I'm a chemist, you can think to make something, but at the end of the reaction, you don't usually end up. This is not, this is true for chemicals, but these materials are, they are made of chemicals, but not easy to make them. So the problem is we cannot really control their design. To some degree, we have, successfully synthesized, for example, gold nanoparticles here. We control this. We have some control over some of them, but not, most of them we don't have the control over this. So, the idea is we like to use these materials and we like to make them safer, right? Where to interfere. So, okay. So let's take a look at the parameters influencing this toxicity of these materials. Size. Do we have a control? So. But not all the time. Shape, the same problem there. Not easy to control. And its chemical nature, yes, we can control. It's carbon-based. If it is, metal oxide whatsoever. Then dissolution and degradation, it's another not really controllable parameter. But, and surface chemistry and reactivity. Reactivity, I just edit this because, I'm a chemist and I have, we have a definition of reactivity, but I don't want to go into this because, for a reactivity, to define the reactivity, two reactants should react. Okay, and if something has to come to the surface of these materials because that's the interface, right? This is why we are interested in, changing this interface. But we don't have much choice to interfere with this. So that's why I am going to talk about surface chemistry here. I don't know if you agree with me. Just tell me, after this talk, we can talk about this. Is it really, do we have much choice to interfere with this? The whole process except surface chemistry. Well, because once you decide to change the surface, that interface between biological systems and these materials, and you need to choose the surface modifier, what kind of molecule you like to attach to surface, okay? And what kind of chemistry you plan to do that. So there are so many, again, considerations here that, for example, proven biocompatibility for application concerns, stability in formulation, because we like to use them in something, right? So is it going to be compatible with what you put in there? Or chemical suitability, is it really, because sometimes, metal oxides are not good in polymers. You cannot just put it in there. So, and low cost, because cost is really important here. And in applicability, there are many things here. I don't want to go through this. And the toxicity concern, dissolution size, blah, blah, blah. We can keep talking about this all day. I don't want to, bore you here too much with this. Okay, the chemistry. Okay, we need to be careful with this again. I'm showing this here for carbon-based nanomaterials. And here I'm showing some molecules that I use during this our project to modify the surface. And the reason I picked, for example, these amino acids, and we didn't use peptides, but we used carbohydrate monosaccharides, because because they're biological. Okay, we can do easy chemistry. They're small molecules; they don't influence the function of these nanomaterials, and we had to choose the proper chemical route to make the surface more suitable. Okay, so here's the deal. And now, what kind of surface it is going to be? And actually, we need to look at the literature and our experience. Okay, then let me move to the next. I have some examples here, because there's so many questions, so many uncertainties here. We can't talk about this all day. I don't want to keep talking, because I picked this zinc oxide here because this zinc oxide is one of the materials widely used in I think in pharmaceutical industry and also cosmetics, right? Because the zinc is important ion for biological systems. We need that. I use zinc. I don't know if recently they became popular now, more soluble zinc. You can take a pill, you feel, it improves your immune system's strength though. So this is, for example, look, what we did, we did this earlier, some years ago, but we these two types of zinc oxide from two different companies we received during our Nano My6 project last, 10 years ago, maybe. Okay, so we tested this but we didn't know what was on the surface of this metal. Somebody made this, they sold it to the companies, and they used this in their products. We had no idea. So we tried chemistry on this, but it didn't work. So we came up with some ideas. We wanted to clean the surface of this, whatever is on the surface of these zinc oxide crystals, particles. We came to the conclusion that we can use hydrogen peroxide to increase the hydroxyl groups on the surface. That was the idea. So we did that, and these two T and P, you're referring to different companies. But anyway, we did all these procedures, and we studied all these things, and I'll show you the results here. Rust production, membrane damage, and mitochondrial activity here. It was definitely, there was a huge difference before and after treating with hydrogen peroxide. I know why this could be, because this zinc oxide is toxic through the zinc ion release most of the time. Okay, so also size and other things, how they approach the cells and so forth. There are many factors here, but this was it. Then what we did was we just wanted to modify the surface further. We put a silica layer. We just like to stop the release of zinc ions. Then we modified the surface further with proteins. That was maybe a bad idea. I just wanted to see, because, proteins, if you modify the surface of these nanomaterials with proteins, they don't like to interact with cells very well. Okay, so because proteins are negatively charged, so cells don't like negatively charged species, because that's why, proteins are always outside, in the extracellular matrix or in the blood and so forth. But here's the deal, what happened? Because we compared this with after modification, there's a drastic difference. So it works. So this is the first example, surface chemistry works. Okay. So the second example, for example, this one, I picked the terrible materials, okay? To show you, one of these materials was, carbon nanofibers. I don't know. You tell me what you think when you look at these materials. But they say it works in their products. I don't know. But they are asking us, Commission is giving us money to make this safer. So I can pick a very nice particle, very controlled, and gold nanoparticles, and I can make different sizes and so forth. But not every material is. We are lucky to synthesize such every material. Look at this. But after surface, we modify the surface of this material, glycine, glucose, and this is, I can't see, it's a disaccharide, and this is diethylamine. Look how they, make the difference. Look at, at the bottom, you see carbon nanofibers are very toxic, but look at this one, for example, glycine modified makes a big difference in all these different cell lines here. So it's not a very huge improvement, but it is something. I don't know. You decide. Let's move to the next example here. Look at this is silicon oxide. This one of the companies are making this for medical use, though. And this surface is silicon oxide is naturally hydroxyl groups on the surface. That's what you expect, right? And then the other is modified with amino groups on the surface. Look at the differences. It's huge. You may ask me, how about these? Look at these images. Are they really, materials or micromaterials? The point here, surface chemistry, regardless of how, bad they look, size-wise or shape-wise, it improves. So, and my point here is that we don't have much choice to, design this. I don't know if there's anyone who can design this material safer. Come to me, I'll talk to you. I think that is the only way to improve a little bit. I'm talking about, of course, there's some certain materials you can really interfere with it, make it safer or so forth. But that's my argument. So, I mean, there are some, I said it works, but a lot of uncertainties, okay? Also, this is from the material. This is at the bottom, right? We are at the bottom. Material, we are making chemistry. We are thinking, quantum physics and, how these nanomaterials, we are at the bottom. So most people talk about the branches, outputs. Okay, they have a different stuff. I can't do that. I mean, I'm very weak with the all those, what is happening outside at the bottom. This is what is happening. Not much, but a lot of uncertainties. Next step is testing. It's another huge thing. So then finally, I will, of course, show my institution and the people who worked over the years on these projects. And I would like to thank them. And this is the curtain I'll leave you. Then thank you very much for your attention.
Thank you, Mustafa, for this presentation about surface chemistry. We have time for one question before we go to the coffee break.
Thank you. Very interesting presentation. So spanning from bulk surfaces functionalization to nanoparticles functionalization, this is the frontier for sure. One question related to the functionality preservation after coating of the nanoparticles. I assume that the zinc oxide functionality addressed was antibacterial or something like that. By making it safer, is it still functional?
No, that's not. Because that, the idea there, I was just trying to, because it's, we published this in 2016. I was trying to prove it makes a difference. We stopped the ion release, it works. So, but of course you lose the function. So how to deal with this? I don't know. I mean, you cannot really deal with it. If you like it to use it for antibiocidal effect, you have to use it like that. So is it toxic? Yes, it is. I mean, but here's the deal. I mean, because we use many different types of the toxic things, what we eat today at lunch, how could you be sure that it is not toxic?
Well, this is a perfect handover because we are about to have coffee break now. Thank you, Mustafa. I'm sorry to cut further questions. Mustafa is available also in the coffee break. And before we all go to the coffee break, quick announcements. So I already said there is a book of abstracts online. I'm not introducing all the speakers extensively with their CVs, etc., because it would take so much time. But please have a look at this book of abstracts if you want to know more about them and their talks. Then already said also the session recordings and presentations will be made available if the presenters agree. Then please have a look at the project corners outside and check the materials there. Then also please use our photo frame and use the hashtags here. And for speakers and panelists, we have small thank you presents. Make sure that you collect them at some point. And before you leave, give this lanyard back to the raffle and you can also win something. Okay, let's continue with the next session. I kindly ask everybody to take a seat and stop chatting. Now we move on with the next session, which is about safe by process design. And as you can read here, the session will focus on safe by process design as a way to assess, prevent, and mitigate release and exposure to advanced materials throughout the product's life cycle. We have 3 presenters in this session. And it's my pleasure to introduce Wouter Fransman from TNO in the Netherlands, our first speaker. And he will talk about safe by process design to mitigate exposure to advanced materials.
So this is the kind of pictures that I wanted to show you. Obviously, you know that we cannot, unfortunately, not substitute or replace or eliminate all the hazards in the world. And luckily, also the JRC acknowledged that. So obviously, the first step is to go for safe by material design. So try to mitigate the hazards as much as you can. But any remaining exposures still need to be assessed and hopefully also mitigated. And this is not new. This has been in the hierarchy of control for many years, at least in occupational settings, is that you try to eliminate and substitute the risk first. So try to remove the hazard, try to replace the hazard. But if that fails, the second step is still to try and isolate the human being or the environment from the hazard and implement control measures and try to reduce exposure. And that's why in the SbD for Nano project, we also took a very similar approach as for the other NMP 15 projects that we'll present later on, is that apart from toxicology, performance, cost, also exposure is a very important parameter in the overall SSbD framework. So when we take the let's say the easiest or the biggest simplification of an exposure assessment model, there's always a source that emits some sort of a substance into the air, and then there's a receptor, the human being or an eco environment that receives, let's say, the decontamination. And when we talk about trying to mitigate exposure, obviously you could control any of these parameters in the exposure assessment framework. But when we talk about by design, at least my interpretation of by design is that you try to do that as close as possible to the source. So providing all human beings with a respiratory protective equipment, in my view, is not safe by process design. It is obviously a way to control exposure, but we try to still control the source of exposure. So we focus on release, emission, and the localized controls that really control the source to avoid any confusion. So when we started off the NMP 15 SbD for Nano project, and I hope you all had a chance to have a go for the booths outside and get some information there, we were set out with the objective and tried to find ways to mitigate and reduce the exposure level, so safe by process design. And to do so, we felt that we needed to identify the stakeholder needs, but also the data gaps and the release and exposure measurement data, because we felt that these were very scarce, and if we can combine them, maybe we could do something useful with them. Based on these data, we developed an exposure assessment model, which was used to assess the current situation, so the exposure scenario that you had within the life cycle of the product, and obviously also alternative exposure scenarios that had a lower exposure to try and compare these in terms of SbD. Release hotspots, very important thing in let's say the mass flow of a material in a value chain. There is always releases throughout the whole process, and it's important to identify those along the whole life cycle. And obviously the most important things, at least in my view, are the final one. So the most effective ways of trying to prevent and mitigate exposure, and providing sufficient guidance to whatever user of the online tool or the system that you use, so that people make the right choices in designing their process or redesigning their process. So first of all, we identified data gaps, as I said, so gaps in measurement data, release data, but also gaps in knowledge, in wishes, in stakeholder needs in terms of safe by process design. And considering the time, I will not go into detail in all of us, but this formed the basis for us to generate new data, so to try and fill the data gaps. And you've probably heard of the eNanoMapper database before, which contains a lot of measurement data, tox data, and therefore we generated new data, and mostly ECHA did this in Spain in their exposure chamber, is doing experiments on release scenarios, exposure scenarios that we felt from the data gap analysis that we lacked data of exposure. We did the data generation, we put those data into eNanoMapper, and then based on the eNanoMapper, we built our exposure assessment model. So it was let's say a data gap analysis, which was from literature data from previous projects that were already in the eNanoMapper database, and generating new data in the SbD for Nano project. And finally, this, I don't think it's working, but yep, okay. Finally, this led to the development of the NEQ model, so the Nano exposure quantifier model, in which we generated all these data, gathered all these data that I just showed. In total, these were 131 individual measurements. Doesn't seem like a lot, but in exposure assessments for nanomaterials, that's actually all there is, basically. So we harvested all this information. Different measurement instruments were used to measure the exposure, because as you may know, nanomaterials are not so very easy to measure. They're very small. They come in different size bins, size ranges, and they agglomerate and aggregate over time and over space. So not so very easy to bring all these data together. Then we build a conceptual model and a mechanistic model, and calibrated let's say the conceptual model against the measurement data that we gathered, and we actually found a pretty good correlation or relation between the model assessments and the generated data, which gave us a good feel of the model accuracy, and also identified the model uncertainty that remained in the model after the calibration. So apart from the science, we also developed an IT model at TNO's own Diamonds platform, and made it available through an API connection with the SbD for Nano infrastructure. And it basically is a model in which the exposure assessment can be done in various stages of the life cycle. So starting from the pristine material in the synthesis of the material, through powder handling, liquid handling that contains nanomaterials, and the use phase end of life scenarios in which the product is being handled or sanded or abraded or whatever. And for each of these different activities, several questions are being asked. And if you go into the tool, you can see more detail. And eventually, the calibrated model will provide you with a quantitative estimate of exposure for that specific use scenario that you fill in to the tool. But obviously, this is not only about exposure assessment, it's about SbD. So we try and persuade people to move towards mitigation of exposure. So there's a comparative element in the tool also, in which you can provide a comparative exposure scenario that has a reduced exposure. And actually the tool will provide you with a comparative estimate and visualization of the different exposure scenarios and the percentage of reduction that you can get with that specific adapted scenario. Then, as I showed you in the beginning, the release is very important, because we consider the full life cycle of a product. So not only one activity, but you have to look at the full life cycle. So from the material synthesis into the end of life stages. And this tool, which is also available in our Diamonds platform, but also in the e-infrastructure of the SbD for Nano project, is to provide you with an overview of release estimates throughout this full life cycle. So this is a semi-quantitative, qualitative approach, which provides you with the hotspot of release, where you should focus your efforts on, basically, to have the biggest effect on mitigating your release and hence exposure. Well, then a bit of a sidestep, at least for us, is that we also looked at dermal exposure, because most of the focus obviously is on inhalation exposure for nanomaterials, because that's the most dominant route of exposure. But there's always the consideration, well, is there also potential for dermal exposure? So we developed a very similar tool, not quantitative in nature, but it gives you an indication of whether there's a potential for dermal exposure in addition to your inhalation risk. So it uses the same, let's say, the same structure, the same activity, same source domains, and it subdivides each of these activities into 3 different ways of dermal exposure, which is via transfer. So that's via surface contamination, so contaminated surfaces that are being touched by the skin. Deposition, so that can be from spraying or from dust in the air that deposits directly on your skin, or direct contact, so immersing, for instance, your hand in a paint or liquid or whatever other liquid. That provides you with an exposure potential, and obviously in the end you can also calculate the skin penetration factor and then the systemic uptake. So what the tool does currently is provide you with a few very simple questions, and it gives you an advice or a basic conclusion on whether dermal exposure is of interest for your specific scenario, in addition to the inhalation risk. Well, then finally, the integration of all the information that we harvested in the SbD for Nano project. I already explained you the NEQ, so the Nano Exposure Quantifier tool, which has a baseline exposure quantification of the current situation and an improved SbD exposure quantification that you can compare and see what the effect is of your reducing factor. And then there's an additional SbD module attached to it, which has 4 different compartments or guidance materials. First of all, there's an ECHA library, so a library with effectiveness values of different control measures that gives you a quantitative effect of implementing a specific control measure, like a ventilation system or a fume hood or containment. And it gives you a range of different effectiveness values that you can harvest from. Then ETENA in Spain worked on CFD modeling, which stands for computational fluid dynamic modeling. I will show you a picture in the next slide. It provides you with a simulated airflow and a very nice coloring schemes that can assist you in, for instance, giving training to workers and to people how the contamination can flow through the air. Then we have mainly work from CEA in France, provided so-called ECHA, so guidance sheets in which a lot of information is provided on different control measures to reduce exposure so that people can make the right choices. And in the SbD for Nano e-infrastructure that I think Works will show later today, there's also an exposure directionality assessment, which also provides you with the important parameters that can reduce exposure. So this is what I just promised. So this is a picture of a CFD model. So it gives you a very nice representation of the different air flows. You may know them from the Formula One or any other, let's say, wind tunnel test, but they're also used to model or calculate the different air flows containing nanoparticles or any other contaminant in the air, which can be represented by different coloring. So it provides a very good guidance to users where they should and where they should not stand in terms of exposure potential. We also worked this out in an online tool, which is also available at our platform free of charge, and also through the Nano map or the e-infrastructure of the SbD for Nano project. So this is all can be used as guidance material. Then the e-cards, as I just presented a very small picture of. So this is a larger image of such an e-card. So it's 1 or 2 pages information containing an effectiveness value. So what is the effect of, in this case, local ventilation system? It provides you with the implementation that it can be used for, the costs that are used to implement this measure, and what the target group is. And then there's a lot of guidance material that you can use to make the right selection for the right system. We have in total 13 different of these e-cards for different, let's say, risk management measures and subsystems. So finally, to conclude, and the take-home messages that I think that safe-by process design should definitely be considered as an alternative or an add-on based on the safe-by materials design. So if we cannot mitigate all the hazards and eliminate all the chemicals that we also need for our daily life, we have to consider and trying to reduce the exposure as much as we can. Data are very scarce, so I think we need to monitor more, and the data that we have, I think we should reuse them and combine them so that we can build models as we did that can assist users in making assessments of different scenarios. And we felt that the NEQ model is one way to do it, but my next presenters will also show different approaches. The SbD process-specific modules that's in the SbD for Nano e-infrastructure, but also in the other projects, I think are a good way of providing insight into how you can mitigate exposure, how you can reduce the release. And hopefully the guidance material that we provided and the other project provide will persuade people to make the right decisions in trying to minimize the exposure as much as we can. Thanks very much.
Great. Thank you very much, Wouter, for a very clear presentation, at least for me. Questions?
Thank you. Very interesting presentation and huge and solid, robust framework. Just one question relating to the CFD. So you have a modeling, mathematical modeling tool. How specific boundary conditions and geometry of the room, for instance, of the production premises may play a role in identifying the exposure level? Should be specific models be run for specific cases, or we have somehow reference values? Thank you.
Yeah, very good question. And you're pinpointing, I think, the only downside of using CFD modeling is that it's very specific to one geometry, one situation. And if, for instance, the worker or the person steps back half a meter, the airflow will be different. So I think that's something that you need to take into consideration when using CFD, is that it's a bit of a theoretical modeling. And if you move the tables around, if you move the chairs around, the airflow will be influenced by turbulences and different geometry. And then of course, it all relies on what you put into the model. If that changes, then the calculation changes.
Hi, thank you very much for the presentation. I'm Joonas Koivisto, the next presenter. But in CFD modelings, they are done under static conditions. So that's why you get like these concentration differences. So it's not actually mimicking the realistic scenario where everything is moving and so on. So that's it.
Great. Final question from here. Okay. Andreas wants to chat later with you in the break. Thank you. Thank you very much, Wouter, again. And we continue with the next speaker, Joonas Koivisto, who just already made a comment from Air Pollution Management APM in Finland. And he will talk about industrial-oriented exposure assessment.
Okay, thank you very much. In exposure assessment, the main challenge is that the worker is performing multiple different contributing scenarios during the workday that contains multiple different tasks. And the worker activity is, of course, defining the exposure time in the working area, and it can also impact on the process emissions, what he is processing, doing, and these are affecting on the work area concentrations. And then there can be background emissions. And then each task, they have their own characteristics, and different contributing scenarios have own characteristics as well. So how to assess all these exposure combinations? This is a big challenge, and ECHA 14 requires quantitative exposure estimates for all these contributing scenarios, unless qualitative assessment can be argued, as for example, for low toxicity materials or so. And the new contributing scenario must be created whenever operational conditions are changed, such as task frequency, durations, and so on. And the challenge with personal measurements is that they are very case specific. So they take only one set of operational conditions into consideration, what have been in or during the measurements. And this, of course, results to high number of personal measurements if for example, all the combinations will needs to be considered. And one solution is setting conditions of use and assessing the relevant exposure determinants by using a probabilistic approach. So conditions of use, they describe the operational conditions and risk management measures that are appropriate to maintain exposure at safe level according to ECHA guidance. And operational conditions, they are more or less similar as exposure determinants, physical factors, and they can be categorized to 3 categories related to process emissions, environmental conditions, and personal behavior. And our approach is starting from the process emissions. This is the point of departure for exposure and health effects. And we can use worst case or reasonable worst case conditions to cover as many tasks in a contributing scenario as possible. And then probabilistic approach can be used to identify which exposure determinants are relevant, so they have significant effect on the exposure level. And if we think about the conditions of use, the objective is not to make a precise exposure estimate for a specific scenario and produce accurate exposure levels or so. But the idea is to find the limit which can be still considered as adequately controlled. And of course, a good question is when exposure is adequately controlled. This is not very well actually specified, not even in US, even though this definition, exposure distribution, 95th percentile, and if the exposure is below 10% of the OEL, then it's considered adequately controlled. And this is according to American Industrial Hygiene Association. And and then in ECHA, I think it's a 17th percentile of the exposure distribution and 19th percentile of the exposure distribution. So what is adequately controlled, this should be decided first. And then also we should consider potential allocation factors because in out of work, you can also have an exposure via diet and air pollution, etc. So you may need to have also allocation factors, and this risk characterization ratio of 0.1 may not be enough. And then there can be, of course, some process-specific limits. For example, multiple processes running in the same room, etc. So you may need to have also allocation factor for that to declare that there are no PPEs needed or so. Okay. And yeah, so the current approach based on personal exposure measurements, these are not very feasible for this. And personal exposure measurements are also often like without contextual information. According to EN 689, you should register all the parameters, relevant exposure determinants, but I haven't seen so far personal exposure measurement data that contains all the relevant information, what are specified in EN 689. So it's more like a subjective assessment if you extrapolate from personal measurements to some other workplace the exposures. So we propose approach which is based on emission source characterization and then predict what the exposure is under all scenarios. So this is more generic approach. And then probabilistic approach you can use to quantify the exposure determinants. And then you can focus on only relevant exposure determinants in your safety communication. So this is definitely a benefit. And I will just give an old example from pouring of pigments and fillers in a mixing silo. Here you can see the big bags. We come a bit later back on that. And here you see how the work environment looks. And we use this two-box model to calculate emission rates and then again to calculate the concentration and then specifying exposure levels and so on. And just quickly, there were pouring of these big bags 4 times in task 1, and then small bags titanium dioxide and small bags micromica. And then there was simulated cleaning. So we specified these task-specific emission rates and or concentrations, and then calculated emission rates. And then here you can see the modeling results, and these modelings were performed by using this Exposure Assessment Inc. Or Exposure Assessment Solutions Inc. TEAS probabilistic 2-box model. And we didn't know the exact parameters very well in the workplace, so there are some uncertainties in some of the parameters, like air exchange rate and air mixing between near field and far field. And this is the final simulation result with the exposure distribution because of the uncertainty or the ranges in the parameters. And what can we see from the statistical analysis? This job sensitivity analysis shows that the time-weighted average concentration is mainly caused by micromica. So you want to focus this if you want to reduce. The differences are not in this case so high. And then job sensitivity analysis, it shows that the task 1 is causing highest variability in exposure. So if you want to know better or parametricize better your model, you should focus on this task 1, measure better, characterize better the parameters in that. And then task sensitivity analysis for task 1, it shows that the generation rate, it has a high variability. But this is ending again. And regardless, air exchange rate has a high variability. Is it? Oh, now it's again. It is not a relevant exposure determinant. It doesn't cause any significant difference on the near field exposure. And room volume, okay, it doesn't have much variability, no much effect on the exposure. Near field volume, neither. It's more or less the same. Air exchange between near field and far field is having a high variability, and this is a relevant exposure determinant. So it is in principle specifying how much the concentrations that are released to the near field, near the worker and the source, and then diluted to the rest of the room. And then you can see how for example, beta is this air mixing is reducing the concentration levels efficiently in the beginning and then flattening out when the air mixing rate is increased. And the concentration is of course increasing the near field exposure. Okay, and then if we just look at this more practical way, so we have this is the observed scenario. This is our 95th percentile exposure level or concentration level in near field. And then if we change these different variables, for example, emission rate, generation rate, by a factor of 2, it has a significant impact on the exposure level. If air mixing is reduced by a factor of 2, it has also a significant impact. General ventilation, if it's reduced by a factor of 5, it doesn't have much any change in the near field concentration, so it's not a very relevant parameter. Then I changed a little bit room volumes from 100 cubic meter. Okay, the work is probably not possible to do there because it's a big machines. But anyway, it has some impact, but not very relevant considering this is very small room. And if we increase the room size by a factor of 6 or 7, it doesn't have any effect on the exposure level. And if we apply near ventilation, in this case it wasn't working during the measurements, And in like worst case scenario, it would be 5 times the observed scenario. So we can identify what are the relevant and less relevant exposure determinants, and then we can make the exposure assessment based again on the criteria, apply LEV, and then if we have multiple batches, for example, how the exposure is increased, okay, apply LEV. So target users for setting conditions of use, well, it's mandatory in legislation, but for process equipment manufacturing. So if you can specify or conditions of use for process machines, then it can be used to reduce the EN 689 personal measurements, number of those. And this, of course, reduces safety management costs and improves sales, hopefully. So there is some sort of benefits for process manufacturers to actually quantify conditions of use. And then, of course, the same for material manufacturers when making chemical safety reports, for example, copper industrial, copper or so. And then you can also apply this for products. So you can quantify consumer products conditions of use. And this is, for example, we use this photocatalytic air cleaners. And then we used also, well, now I've been talking about air exposure, but it can be, of course, whatever exposure. So we adopted this basic dermal model developed long time ago, and we applied it for Asina textiles, and this dermal model is based on mass balance principles, and then you can have different release rates. Here we had a textile, and the textile release was measured in LATAT. So by using abrasive test, and this is designed for color fastening. So it's not maybe so realistic emission, or it doesn't describe the realistic emission rate when you wear, for example, silver nanoparticle coated textiles. So it's the test is violent as compared to wearing clothes or face masks or so. But anyway, so you can then calculate the dermal intakes, and you can also, when you know, well, what is the contamination, for example, fingers, etc., after using glass, and then you can use it to estimate oral exposure. And then when you wash your hands, then some fraction is removed from skin, and then exposure is reduced, or the intake is reduced as well. So we use this model for Asina textiles and so on. That was the last. No. And conclusions. Sorry about that. Okay, so we specified this method to quantify conditions of use and relevant exposure determinants based on probabilistic exposure assessment and sensitivity test, and then how to focus only on relevant exposure determinants and so on. And then some examples how it can be applied. You can find these studies are showing the applicabilities. And the drawback here is that emission rates or factors, they are not very often provided or measured, even though the source here is the point of departure of exposure and health effects.
And we may move on already with the last speaker in this session, Jesus Lopez de Peña from Tecnalia Research and Innovation in Spain. And he will talk about digital twin for sustainable manufacturing. Perfect. Jesus, floor is yours.
Thank you so much. So we move to process engineering. So in this presentation, I would like to show you the work done in Asina project to develop a digital system based on the digital twin technology created to improve the process, to optimize the process, and in parallel to reduce the emissions and derived exposure. Okay, how to connect digital technologies and safe and sustainable production processes. So you can see the document published by the European Commission, the Strategic Research and Innovation Plan for Safe and Sustainable Chemicals and Materials. And this document identifies the digital technologies as a driver for clean, green, and efficient production processes. So the idea is to redesign the production processes in order to create or to modify them in order to have safer and more sustainable production processes. Digital twin technology is an important technology that is proposed by the European Commission to achieve the Industry 5.0 paradigm, when we the next production processes, the digital factory, the factory of the future, is will use this technology to evolve the processes and also to create new, safer, and more sustainable production processes. So the concept of the digital twin. What is a digital twin? A digital twin is basically a digital representation of a physical asset. So we can't represent a car. We can represent an offshore oil platform, a building, manufacturing processes, even the human body. So then we can apply this technology to model the different assets and obtain results. In our case, we are going to model a spray coating process for textile. So the three building blocks constructing the digital twin approach are the following. First of all, the real world. The real world is the process itself. The digital representation. In Asina, we have constructed a digital twin, developing new software and hardware elements. And then we have the three component, which is the data flow between the two worlds. So then we update the data of the system in real time, and we can monitor, predict, and optimize the process. So regarding the hierarchy of strategies for process design, so we can consider a digital twin as an active engineering protection strategy. So it is not a pure safe by design strategy, but when the system is operating, so the system is always trying to optimize the process. So this system can provide inherent safety strategies to improve in real time the process. So we can minimize the consume, for example, of hazardous substances, nanoforms, or we can moderate the parameters of the process in order to improve the process and to minimize risk, etc. So you can see in this slide the use case where we have implemented and validated in a practical way our approach. So the hypothesis of Asina is to explore this technology to prevent emission and exposure by optimizing the process. So you can see a typical process, spray coating process for textile. So with two main stages. First of all, the nano coating spraying stage and the drying stage. So, and on the right part of the slide, you can see three pictures showing the process input, the unroll of the raw textile, the spray chamber with the two guns, and the output of the process showing the rolling of the coated textile. So, according to the ISO 23247, so a digital twin for manufacturing can be structured in 4 domains, as you can see in this slide. So the first domain, the green domain, represents the real world, the process itself. The orange domain is showing the digital twin domain, that is the brain of the system, so the digital world. And the device communication domain, D1, is showing the interconnection between the two worlds. And we have a last domain, the user domain, which is the domain in charge to show the result and to connect with the end user in order to exploit the services of the system. So let me show in brief. So the developments carried out by Asina in each of the 4 domains to construct the full demonstrator. So you can see in this slide the first domain, so the sustainable manufacturing domain. So our interest was to prevent, this is the keyword, to prevent and reduce emissions and exposure, air emission and exposure. So we need to capture this information from the process. So we developed a network of wireless monitor system sensor based on low-cost sensor for particulate matter. So we are monitoring different fractions, so aerosol fractions, particle number concentration and particle mass concentration. And then we have developed some specific algorithms to calibrate the system against reference instrumentation. So we developed some campaigns in order to calibrate our network. So then the system, the digital system, can see the concentration of particles in the working environment. We also tested some different types of low-cost sensors for measuring particulate matter in order to see and identify the best solution for our monitoring system. So we tested the plant towers, sensorium, and other sensors. So then we have the first stage constructed. The second domain is related with the connection of the 2 worlds. So then we developed a concentration node. You can see an electrical cabinet that is capturing parameters from the process and also the information from the wireless node deployed in the room. So then we develop also a host for communication in order to have IoT connection to export all this data to the cloud, because in the cloud is the brain, is located the brain of our system. The third domain, so this is the domain containing, first of all, the database with the data from the process and the data calculated and updated in real time by the models implemented in this domain. We have developed 2 models based on artificial intelligence techniques. First of all, the first model is dedicated to predict concentrations of particulate matter. And the second model is dedicated to optimize the process parameter in order to find the best configuration to reduce emissions and exposure, maintaining the quality of the product manufactured. And this is a key point. So we have developed this approach with Python using Grafana as an open source software for data visualization. And finally, you can see the 3 main screens that the end user can use it to monitor the process, to predict concentration, and also to optimize the process. So we can see in the first screen the different wireless sensor deployed in the room and the value and the evolution of the data. In the second screen, we can predict the concentration taking into account the historic data captured by the system. And in the third screen, you can see the current production parameters and the new parameters suggested by the system. We are working in an open loop. That means that to introduce the new parameters in the process, so the operator needs to do it manually. So it is important. Then just conclusions on the value proposition. So we think that this technology is closely aligned with the recommendation of the European Commission to create or to transform in order to have a production process safer and more sustainable by design. So our technology can predict and optimize the process in real time. We can manage emission and exposure through alarms, and we can also work with KPIs. We have developed 3 KPIs. The first one is related to the consumption of energy. The second is the consumption of solutions, so nanoforms. And the third is related with the rate of emission of the process. So according to the recommendation, our technology, our pilot demonstration increase the efficiency in terms of energy and materials, reduce the use of hazardous chemicals, and prevent and reduce also the emissions, the air emissions and derived exposure. So who are the target users of end users of this technology? Or any manufacturing company, regardless industrial sector, so size, manufacturing process, and design stage of the process. So we can customize the approach for any interested company. And finally, it is important to underline some limitations and next steps in this project. So you can see that further development to reach the market is required. So we have developed a first demonstrator. The TRL is more or less 5 to 6. So then it is necessary additional research and additional projects to export the technology and the development until TRL 8-9, so to put the system into the market. So new industrial use cases are necessary. So in fact, we are going to refine this approach in Sunshine project. So it is important to underline the complexity of the industrial scenario. So we need to develop an approach case by case. Like if you are going to manufacture a product, you have a set of receipts, you enter your receipt, and then you manufacture the product. And regarding the low-cost particulate matter sensors, so it is important to investigate the drift of the sensor and also the calibration strategy. So when we talk about one sensor, well, calibration strategy is not a problem. But if we have 100 sensors, we need to develop quickly and cost-effective strategy to calibrate this kind of sensors. So, and that's all. Thank you very much for your attention.
Thank you, Jesus. Yeah, you're addressing the most important part, I think, in the exposure, so the processing of nanomaterials related to the artificial intelligence. According to your experience, what is the volume of data that you have to acquire in order to make predictions on a specific processing environment and conditions? Thank you.
Thank you for the question, Massimo. It will depend of the process that you use to implement the system. So in our case, so the process parameters were the belt speed, spraying flow, I don't know, the height of the guns on the textile, I don't remember, and the concentration of particles in the environment. So we use at least 4 or 5 parameters to train and to obtain data about prediction and optimization of the process. So, but it will depend of the process selected. So, in fact, we detected that the key parameter was the belt speed and not the flow, the spraying flow. So we can increase the spraying flow and the concentration in the room is more or less the same. But if we increase the speed belt, so the concentration is increased. So then I think my suggestion is to develop an approach case by case. So in fact, we can have a general paradigm to implement DT technology for all these issues, but we need to customize the approach to one specific application.
Ottmar Schmidheimer, Center Munich. Thanks for this great talk. Digital twin is a big name for what you're doing. Digital twin would mean that you cover all the details of what you're investigating. And I think you're a bit off in that direction. Could you comment on the perspective of really incorporating the complexity of these issues in your digital twin?
Thank you for your question or for your comment. So I think that I have shown the document from the Commission. So I think a digital twin can be one of the most important tools that we have to improve processes. So then we can apply improvement to improve what you want to improve. So in our case, so let me say the emissions and The idea was to, first of all, to prevent. So I would like to emphasize this word, is to prevent, not to control, to prevent. And then we can reduce and control. So then the future of this technology, for me, is all of them are going to have a great implementation. In fact, we have developed models to predict and optimize the process, data-driven models. So based only on data. So then the idea would be, for example, to create hybrid models, mixing approaches showed in this presentation. So for example, models for exposure, other models, in order to, let me say, to reinforce the approach and to obtain better results regarding the optimization of the process. So I think it can be an idea to evolve in this technology. So hybrid models may be very interesting to improve processes.
Okay, great. Thank you very much, Jesus.
No,
sorry,
Soko is calling.
Apologize. Last question, yes.
Last question, yes. So about the costs of implementing this into into any process or anything is something that is doable for industry to implement this sensor and all this into their process to control and to reduce that, or is out of their costs?
Thank you very much for the question, Soko. So one starting point. So it is mandatory to evolve the current existing processes in order to be digitalized and also to be adapted to the green transition. So you need to implement digital technologies in your process. So then regarding the cost, it will depend on the process. It's not the same a process in SME that a process in a large company. So low-cost particulate matter sensor. So sensor plus the enclosure plus the controller to communicate data. So I think we can talk about 50, 60 euros per sensor. So then if you put 10 sensors, you are talking about 600. So it is not money. So then we have used our own IoT system, but you have your system in your company. So then the idea is to develop models that can be customized to your process in order to optimize the process and prevent exposure. So then it will depend on the size. I can think about, I don't know, a consultancy for 10, 20,000 euros, but it will depend. But the thing that you need to evolve in terms of digitalization, so you need to put money. So if you, in addition to improve the quality of the product, you can develop more sustainable process, it's okay, it's fine.
Okay, great.
Thank you so much.
Thank you very much, Jesus. With this, we also close the session of Safe by Process Design and move on with the next one that is about sustainability, LCA, LCC, so lifecycle assessment, lifecycle costing, functionality and costs. We have two presentations in this session because we are very tight in the time. We already agreed beforehand that this will be without questions. So if you have questions to the speakers that are coming now, please keep them in mind and use the lunch break to engage with the speakers. And the first speaker in this session now is Alina Bisak from ACER in Italy. And she will talk about SbD for Nano production cost analysis of modified versus unmodified nanomaterials.
Thank you, Suzanne, and thank you to all of you to being here and for giving me the opportunity to do this presentation. So today, as Suzanne said, I will talk about cost analysis of modified and unmodified nanomaterials within the SbD for Nano project that Mustafa and Wouter showed you in the presentation above. And the cost analysis is not simple, so simple. So it consists of different steps. And here I try to report all of them. Today, I will focus about the cost of compilation and the cost analysis. And I will start with the first step of this analysis. At the beginning, for the realization of the cost analysis, we divide the cost in different categories and ask to all of our industrial partners to compile the file and to give us the results, information about this type of cost. And they provide us the results, and then we compared modified versus unmodified, the price of modified versus unmodified nanomaterials. But what's wrong with this kind of approach? This kind of approach is so specific. You cannot use for other type of analysis. So it is specific for each case study. So within this project, we like to generalize the cost and to make something that is not so specific. Everyone with its own experiment that can use an approach, a file, a method for calculating the cost. So in order to generalize this analysis, this type of analysis, we took internal inputs, external inputs, or information from scientific papers and website, and develop a file that is not working here. It's a video. Okay. Okay, I'm sorry. Okay, it should be a video in this presentation. It's not working. Okay, we develop. Okay, I try to explain. We develop a file that is an Excel file. Is an Excel file that allow to calculate the cost for a laboratory scale and an industrial scale. You can use this file for the calculation, for the prediction, for obtaining the prediction of the cost of the previous categories that I show you. And we use that file for the calculation in two of our industrial cases. And I will show you indeed the results of a case study on laboratory scale and then industrial scale. I will start with the example of Axon, which is one of our industrial partners that produce nanoparticles for fluorescent measurements. And we use the file to estimate the cost for the producing of gram quantities. And why we stay on gram quantities? Because they use the gram quantities is enough for the realization of millions of samples. So in this case, we can calculate the cost on gram quantities because few quantities of materials allow to perform a lot of fluorescence measurements. And yeah, we use the file that I mentioned before. And as you can see, we were able to estimate the cost for different produced quantities. And yeah, as you can see, and as we expect, lower quantities of nanomaterial cost more than producing higher quantities of that kind of nanomaterials. We have a decrease in cost with the increasing of the gram produced. And then we move also on a kilogram scale, because we cannot talk only about the gram scale when we talk about nanoparticles, production of nanoparticles. So we use that file also to predict the cost for kilogram scales, starting from, also in this case, gram productions of titanium dioxide modified titanium dioxide nanoparticles. These nanoparticles are produced from Creative Nano, another industrial partner of our project, and they use Creative Nano use this type of nanoparticles for the producing of photocatalytic and easy-to-use coatings. So at the end, they mix nanoparticles with the painting for obtaining these photocatalytic coatings. So as you can see here, for example, for 1,000 kilograms of paint, there are need about 5 kilograms of nanomaterials. So our industrial partner, Creative Nano, give us information about the cost on laboratory scale. More or less, we are talking about grams, few grams of nanomaterials, and using the file that I mentioned before, we were able to predict the cost also on, it's not industrial, but let's say pre-industrial scale. And also in this case, you can see that the cost per gram of nanomaterials is about 12,000 euros per kilogram, 12,000 euros per kilogram. While increasing the produced quantity, we can decrease the cost. And also in this case is what we expect when we want to move from the laboratory scale to the industrial scale. And what you have to take home from this type of analysis is are not the numbers itself, but the trend in the decrease of the costs from laboratory scale to the industrial scale. And yeah, this is all. Thank you for the attention.
Yeah, okay, hello. So yeah, I would like to present the approach that we have proposed within the Sabina for a simplified, wait, yeah. No. Okay, for a simplified cost and sustainability assessment within the platform. So the idea is to have a set of simplified tools that enable to have an overview, a preliminary overview of the environmental impact and cost balance of the use of nanomaterials in certain products. This means that, for example, because we add some new material to a product, we are adding, we are causing some, I don't know, global warming potential emissions or even toxic emissions, either in the production, in the use phase, and so on. But at the same time, it may happen that we are making the life of the product longer, that it's self-cleaning, so we don't consume water during the use phase, and so on. So we want to have an idea on how this balance gets on from the sustainability point of view and also from the cost point of view. So we have proposed these simplified tools focused on two sectors, additive manufacturing and paint sector, because they are the main goals of the Sabina for the demonstration. And we have proposed a life cycle approach. So basically for the sustainability assessment, we propose a simplified life cycle assessment tool. And since it's intended to be able to use it even early in the design phase, we have added several simplification resources, including to be able to model different scenarios, to use minimum and maximum values, because very often we don't have the absolute value, not even at the end, but less at the beginning. So with this information, these tools, what they provide are 4 life cycle assessment-based impact category indicators, like global warming potential, cumulative energy demand, toxicity and freshwater ecotoxicity, and also some cost assessment results, like the influence of different cost elements in the final cost for its application, and also relative cost, comparing different scenarios, for example, a base case and up to 4 additional scenarios. Oh, sorry. Right, okay. So we'll have these tools within the Sabina platform in the cost and sustainability assessment part, as you see up there. So there will be 2 sets of interlink Excel files, where you have a main Excel file where you describe the main scenarios, characteristics, materials, where it's going to be used, how long it's going to last, whatever. You can refine its scenario and see specific results for its case, and then you can have summarized comparative results in this additional file. So that means the idea is that the user has to input as less as possible information, at least at the beginning. It's everything open so that the user can implement more information if he or she wants more detailed information that is different from the background data that is included. But so the minimum data would be like the materials used in the product, both nanoforms, but also other materials, conventional, I don't know, polymers or whatever that is being used, the process steps in the production, which emission control measures are being taken, whether a product is going to be applied indoor and outdoor, how long it's going to last, which is the foreseen end-of-life scenario, and the main cost elements of the production. And with that information, we have added some background data that enable the calculation of these indicators that I presented before. So we have information regarding life cycle assessment data for materials, processes, energy resources, I don't know, transport steps, end-of-life phases. So when we select that we are going to use, I don't know, polypropylene or whatever material, we already have in the background, which are the contribution to this global warming potential, toxicity, ecotoxicity, and so on of these materials. And the same with all of the processes, energy resources, and so on. That means that there has been an extensive work also reviewing processes, materials, what is already calculated, inventories, and so on. And for more new, let's say, processes like additive manufacturing processes, we have done an extensive review of which are the energy consumptions, the additional materials that are required, material losses during the processing, and so on. And the same, we had to compile, as I said, general life cycle assessment data for nanoforms and for conventional material. For conventional material, there is quite some information, although we wanted to stick to the open source resources. And for nanoforms, we have to also compile a lot of information from literature to see which is their contribution to the different impact categories. Apart from that, this background data includes also potential release over different production steps, use and end of life. Also how the different ventilation or control measures affect to the release. And of course, how the emitted or potentially emitted nanoforms may affect to the environmental impact in terms of toxicity and ecotoxicity. So we have done a review of existing characterization factors. This is the term that we use in life cycle assessment. And we have tried to be more accurate with some specific nanoforms within the project based on the specific toxicity and fate data. So another issue that is important in this tool is the performance, because I said that is what makes the balance change. It's not only the impact associated to the materials at the release, but also what we gain with that. If the material lasts longer, if it's lighter. So if it's going to be used in transport, there will be less impact in the transport associated. So there is a possibility over the use of these tools to include this kind of information. Either when we model the production process in terms of material required, when we model the process steps, because perhaps we may use lower temperatures, therefore lower energy, either when we model the use phase in terms of cleaning steps and water resources used or potential emissions, in the transport steps, if it's, for example, going to be used in transportation means, of course, in durability, which is very important. And we have added also some potentially adapted factors to make this equivalence, let's say, to calculate this balance. So with all this information, at the end, the tool provides, let's see if I manage, the tool provides some results in terms of these 4 types of indicators. And for each one of them, there are minimum, average, maximum values, which in this case are not so far from each other, but in some other case can be a very high variability. So very often the result will be that we have to dig deeper into the data to get better results. And you may have, for example, also some results of relative cost comparing the different base case scenario with other additional life cycle scenarios. So I hope I wasn't over time. Thank you very much. And thank you for all the Sabina project also.
Great. Thank you very much for your presentation. Thank you. With this, we already move on with the next topic, which is about legal aspects of Safe by Design. And we have again 2 short presentations. The first one given by Anthony Bonchon from GNS in Belgium. And he will talk about legal aspects and challenges of SSbD.
Yes, good afternoon, everyone. And thank you for giving me the opportunity to present very shortly some considerations about the legal aspects of Safe by Design and now Safe and Sustainable by Design. These considerations have been developed during the last 3.5 years in the context of the project SbD, which has also a workshop on this Thursday morning. I will quickly just remind you what you probably know, and it was very interesting to listen to the other speakers this morning because they've really paid the attention to the meaning of what by design exactly means. And legal systems, they are about words, the understanding of words, the interpretation of words, and of course, the language is extremely important. And it is important to point out that until the Commission recommendation of the 8th of December 2022, there was no legal text speaking about Safe by Design and now, of course, Safe and Sustainable by Design. What we lawyers do is typically we make a textual research. So we use search engines, and on that front, of course, artificial intelligence is now playing a bigger role, but still we look into the text, the legal text, and we try to find occurrences. Do European law text speak about Safe by Design? And there were only 2 occurrences at that time when we started the project. And it was very interesting to see that words have been used without having any definition. So of course, we have words which are used, which can be interpreted without any further legal content behind the words. And so, of course, what we did in the context of the project was first to dig into the deeper foundations of EU law and to understand what is at stake when we speak about Safe by Design. And the first principle, which is very obvious, at least for lawyers, and which is often subject to a misunderstanding, is the precautionary principle. The precautionary principle, contrary to what some scholars or other stakeholders may say, does not prevent innovation. On the contrary, it brings a balance of interest on its own. And it is very interesting to take that into account, that the precautionary principle calls for a balance of interest, but of course, balancing interest, which could be on one end about innovation, taking risk also for human health, environment, business risk, but at the same time we have to protect, of course, a certain number of interests. It is, of course, very important. The health policy, consumer policy are relevant, but what was interesting and what we found as being a relevant comparison is the fact that in a field which is, I think, known to everyone, at least because I think all organizations have to comply with that, is personal data protection, the famous GDPR, General Data Protection Regulation. And it is interesting to see that when in 2016 the European Union decided to adopt a regulation which harmonizes the laws between all the member states, it implemented a privacy by design principle, which had been discussed for more than 20 years by the legal scholars and the privacy community. So it took more than 2 decades before it became hard law, that is to say, law that can be enforced and that stakeholders, the addressees of that regulation, have to comply with. And so we have found a very interesting comparison, and which inspires, of course, about the future potential developments of Safe by Design and now Safe and Sustainable by Design. We've also looked at other legal systems in Asia and the United States, but we came to the conclusion the European Union is well in advance on that front and also from a legal perspective. Of course, the recommendation changed, of course, the perspective, because a recommendation, as you may know, is a legal source. it is a legal source. We don't speak about guidelines. Recommendation is one of the 5 legislative sources of the European Union, but, and this is important to note, it is not legally binding. This is the particular nature of some legal instruments of the European Union. It is not legally binding. And so, of course, as you know, the recommendation implements a voluntary scheme. And so, of course, we go back to the question about how can we basically have a scheme which is purely voluntary. There is not yet a legal definition. I mean, like when you have one in a legal dictionary, you don't have a legal definition of safe and sustainable by design. You have a whole description of what it can mean, 2 stages, 2 aspects to take into account, or methodology, but you don't have a legal definition in the sense of a definition you find in directives or regulations. And therefore, there remains a certain number of legal challenges. Of course, challenges about the effectiveness of soft law instruments, because it remains a soft law instrument in the sense, if you do not comply with the recommendation, well, fine, you do not comply. Of course, it's a matter of public perception, and this is, of course, something to probably monitor. The access to data, well, it is extremely interesting, and this is the very nature of legal systems, is that it can evolve from one second to the next one. This very morning, the Court of Justice of the European Union in Luxembourg issued a very important judgment because it set aside a Commission decision just this morning which prevented the free access to harmonized standards. So probably go on LinkedIn. I will post something on my LinkedIn profile later today about it. This is a legal earthquake because it means that all the standardization bodies, normally, if they want to comply with what the Court of Justice decided this morning, they will have to give free access to harmonized standards. This is a big change in terms of the whole economics of standards, of harmonized standards. So, of course, this is one of the key problems with, of course, safe and sustainable by design. How do you get access to data? And especially in a free market economy. This is, of course, extremely important, and when data is extremely important. The question of the benchmark is also remaining challenged against what kind of state of the art do you evaluate? And this goes back to the question, if you go to the design stage, what do you have to take into account, really? And of course, one of the biggest challenges, in our opinion, was in SbD, is there any potential of a liability shift? Because we speak about a by design approach. Does it mean that liability will now change and will not longer be put on manufacturers, but rather on innovators? And basically, after the single legal workshop SbD, we came to the conclusion that in the current state of the safe and sustainable by design approach by the European Union, there won't be any shift of liability. So inventors, scientists, don't be afraid. You won't be held liable, of course. And I think this is an important message because, of course, these words could have a different meaning, but we considered that, of course, we have the development of a whole family of by design principles, privacy by design, SSbD, banning by design in pharmaceutical legislation, circular by design. But of course, there is, in our opinion, no liability shift for the time being. And this is a conclusion we will much more develop in the workshop on Thursday morning. Please be welcome to attend it. Thank you very much for your attention.
Okay. Well, thanks to Anthony for giving an introduction to the what I call the hard drivers, or perhaps lack of hard drivers for SSbD. I want to give a quick context for the work that we've done in the SbD for Nano project. Our task originally was to look at the integration of the results from SbD for Nano into the Nano Risk Governance Council that was being looked at by the NMBP 13 projects. Now, obviously, the Nano Risk Governance Council rather slipped to the wayside, and we had to have a bit of an emergency change of direction for our task. So what we actually looked for was actually just taking a much more a high level approach of, well, why should anyone actually adopt safety by design? What is there for industry in particular to do? Because frankly, safety by design, SSbD, it'll only be successful if it's adopted by industry. Because they're the innovators and obviously researchers as well. They're the people who are going to be actually employing it and making the difference. So we sort of want you to look at, well, if, say if there is potentially at the moment not necessarily that many regulations that apply to the innovation process. Perhaps not surprisingly, because I imagine it'd be extremely difficult to design a useful regulation that would do that very easily. So I would say regulations are hard drivers. They're things that you have to do, and they're things that your competitors have to do. So everyone's on roughly the same play field. Whereas I'm talking about soft drivers, which are more optional. And if you adopt them, it doesn't necessarily mean that all your competitors are going to adopt them. So you may well think, well, why am I going to go and commit a load of resources to put do SbD, SSbD, if all my direct competitors are not spending that money? So just say this is just a bit of an amalgamation of the Nano Reg 2 results along with the Cooper stage gate model, and then looking at what I would say very broadly is where regulations fit in. So a lot of the submissions really only occur immediately before launch of your product and moving into commercialization. There are some regulations that will apply to everyone, but it's generally around things like notifications, CLP, that side of things. So what I try to look at what the economic drivers. And one aspect of perhaps, these are the sort of things that perhaps you, as a researcher, you could present to your CFO, your CEO, and say, this is why we need to spend the money, the extra money. So one aspect will be avoid late-stage product failure. If you get through your research process and right at the last minute, you suddenly find out your product's toxic, and you can't put it on the market, you have committed an awful lot of money and resource into the process. And it's harder and harder to change your product as you go through innovation. So very much people sort of look at the people looking at innovation, really push this fail fast, fail often, which means get rid of all the options as quickly as possible, all the ones that might not work quickly as possible. Just leads back to something that Mustafa introduced with his surface functionalization. I noticed that one substance that was being looked at as functionalization was ethylene diamine. Now, from a regulatory perspective, that's an SVHC. That is potentially going to be authorization. It's a skin sensitizer. It's a respiratory sensitizer, potentially. That would, in my view, flag up some massive red flags immediately. I would be either wanting to even just kick that out immediately from my research, or if I do want to carry on with it, I want to make sure that when I've done the functionalization, my product doesn't also have the same potential effects. So this is something that could be flagged up extremely easily. You don't want to be getting through to 2 years worth of research, think you've got a wonderfully good process and suddenly find out your product is a respiratory sensitizer because of the ethylene diamine. Oh, sorry. Then other aspect is regulations. They can put a very large economic cost all at once. So for example, REACH. You do your REACH registration once you go over 1 ton of placing a substance on the market. Now, if you've merrily gone and done all your design, not thought about safety at all, you may well get to the stage of suddenly just going, right, just to the point I want to do commercialization and get all my sales and marketing people doing all their stuff, you've suddenly gone and got potentially 100,000, 200,000 euros worth of testing costs. Now, for a small company, that could cause some serious cash flow concerns, because obviously cash flow is really important to a small company. It's not necessarily just over the long term. You need to make sure you can pay your staff in the few month to month. So you've got to make sure you have cash flow. So my thoughts would be potentially, if you can introduce safety by design, perhaps spend a little bit more money early on and generate data that's not necessarily going to be your regulatory submission, but perhaps supports your regulatory strategy, perhaps supports your read-across arguments to use existing data. For nanomaterials, supports your argument to put something in an existing set of similar nanoforms. So actually to generate that data while you're doing SbD, so it's actually, say, useful from a regulatory perspective. But I'm not saying it's going to be your actual key study in your regulatory, because obviously those have to be done with validated methods. And as we've seen, there are not that many validated methods. There are a lot of more options available if you don't just stick to validated methods. Look, there is a consumer willingness to pay for safe products. These are extracted out of journal articles. I'm not so sure with the cost of living crisis whether this will still be the case. Clearly, the consumer is rather fickle and has different. Their buying decisions change. There are social drivers to adopt it as well. So moving away from just the company and maybe to a more sort of social aspect. We know about the issues, the massive potential social costs that arise from chemicals, and they're unfortunate. As we're limited for time, I won't go into too much detail here, but these are all estimated costs from certain chemicals. And I would argue that all three of them, potentially, if SbD had been put in place, could have been at least potentially predicted and investigated perhaps in more details. PFAS, carbon halogen bonds, are known to not be very biodegradable. Chloropyrifos, it's based, same family of substances as nerve gases. Lead, what potential downfall of the Roman Empire. So those are sort of very, very basic sort of red flags. I would also argue that potentially adoption of SbD could possibly accelerate the adoption of NAMs and regulations, and much because it's a potential way of generating data. I would also say that one potential issue about the adoption of NAMs might well be that even if a NAMs gets validated and a whole protocol gets validated and regulatory accepted, unless contract research organization can find a commercial reason to offer it, then it'll just sit there on the books and potentially no one will use it. And obviously, CROs need to have a demand. And what I'd potentially say is potentially SbD could generate that demand that will then enable them to argue that they can then provide the supply. So this is sort of potentially arguments towards that. And my final things that potentially to drive more social aspects of that's SSbD is the drive towards green chemistry, circular economy, all these different things that I mentioned in the strategy for sustainability. But beyond that, manufacturers and retailers, they are committing themselves to adopting green chemistry. People like Walmart are really putting these in their actual basic company policies. They want to go to that. Well, if you are wanting to supply to a retailer such as Walmart, then they will want at least some evidence that, yes, you have actually thought about green chemistry. And I'm going to move now back once again to Mustafa and give him a plus point. Or that's what it is. They're looking at these proteins, carbohydrates for surface functionalizing agents. Those, in my perspective, look as though they would really fit in nicely to the green chemistry perspective. And what I would argue here is that safety by design can generate the data to actually be able to allow you to justify an argument of being able to supply to a company that really wants to see green chemistry being adopted by their suppliers as well. I think I've probably just slightly gone over 7 minutes. Just thank you for all your attention, and thank you to partners on the SbD for Nano project, in particular IOM, BNN, and TNO. And I apologize if I've missed anyone else. Thank you.
Great.
Can I just say, go to the SbD for Nano booth outside there. There's more detailed fact sheets. Potentially, if you want to go and think, yes, I need to provide this to my CFO, you could. They're really simple, basic approaches that you could go and try and present an argument.
Perfect. Thank you so much, Neil. And with this, we can already close the session and go into the lunch break. We have a slight delay, but we have planned to be back at 2, and I hope this is still enough time now for everybody to have a decent break, enjoy the lunch, have a coffee, chat with people, network, and see you at 2 back here. And the speakers, please come to the stage.